Welcome to today's session. In this problem, we'll dive into problem number 2150, find all lonely numbers in the array. We'll explore different approaches to solve this problem effectively, including a brute force method. Let's get started. In this problem, we are tasked with finding all the lonely numbers in a given integer array called nums. A number is considered lonely if it meets two specific conditions. First, it appears exactly once in the array, and second, none of its neighbors, meaning the numbers immediately before it, x1, or after it, x plus 1, exist in the array. The goal is to identify all such lonely numbers and return them as a list. The output list can be in any order, so the sequence in which the lonely numbers are returned does not matter. For the input, we are provided with an integer array nums of length n, and for the output, we need to return a list of integers representing the lonely numbers we've identified in the array. To better understand the problem, let's look at an example. If the input array nums is 10, 6, 5, 8, the output would be 10, 8. Here's why: the number 10 is lonely because it appears exactly once, and neither 9, 10, 1, nor 11, 10 plus 1, are present in the array. The number 6, however, is not lonely because it is adjacent to 5, 6, 1. Similarly, 5 is not lonely because it is adjacent to 6, 5 plus 1. Finally, 8 is lonely because it appears exactly once, and neither 7, 8, 1, nor 9, 8 plus 1, are present in the array. Therefore, the lonely numbers in this case are 10 and 8, which we return as the output. Now, let's consider another example for more clarity. If the input array nums is 1, 3, 5, 3, the output would be 1, 5. Here, the number 1 is lonely because it appears exactly once, and neither 0, 1, 1, nor 2, 1 plus 1, are in the array. The number 3 is not lonely because it appears twice in the array, so it fails the condition of appearing exactly once. Lastly, 5 is lonely because it appears exactly once and neither 4, 5, 1, nor 6, 5 plus 1, are present in the array. As a result, the lonely numbers are 1 and 5. Additionally, it's important to consider constraints and edge cases. For example, if nums contains only one element, that element will always be lonely since no neighbors exist. On the other hand, if all elements in nums are repeated, the output will be an empty list. With the size of nums and the potential range of values being large, the solution must be efficient to handle up to 100,000 elements and values up to 1 million. To begin understanding how we can solve this problem, let's first consider the brute force approach. The idea here is straightforward. For each element in the array, we check two main conditions. First, the element itself must appear exactly once. Second, neither of its immediate neighbors, the values one less or one more than the element, should exist in the array. To achieve this, we would use two nested loops. The outer loop would iterate through each element in the array, and the inner loop would handle counting occurrences and checking for neighbors. While this method is simple to implement, the downside is its inefficiency. For every element, we repeatedly scan the array, resulting in a time complexity of n squared. This makes it impractical for large input sizes, where performance becomes a significant concern. The simplicity of this approach comes at the cost of being computationally expensive. Now, to address the inefficiencies of the brute force method, we can turn to a more optimized solution using a hash map. The idea here is to use the hash map to store the frequency of each element in the array. This allows us to consolidate the work into two passes. In the first pass, we iterate through the array just once to populate the frequency map. Then, in the second pass, we iterate through the keys of the hash map, checking the loneliness conditions for each key. Specifically, we verify that the frequency of the element is exactly 1, and that neither of its neighbors, one less or one more, exists in the map. This approach reduces the time complexity to n, because the operations for counting and checking conditions are linear. However, it does require additional n space to store the hash map. This trade-off is worthwhile, as the efficiency gain in terms of time complexity makes the solution scalable, even for larger inputs. An alternative strategy involves sorting the array first. By sorting the elements, we can simplify the process of checking the loneliness conditions. After sorting, we can iterate through the array and for each element, ensure that it is distinct by comparing it with its adjacent elements. Additionally, we check whether its neighbors, the values one less or one more, are absent from the array. Sorting the array requires O, n log n, time, and the subsequent iteration is linear, resulting in an overall time complexity of O, n log n. While this method does not require extra memory for a frequency map, it sacrifices efficiency compared to the hash map-based approach. For very large arrays, the increased time complexity becomes a limiting factor, making this method less optimal in those scenarios. Among the approaches discussed, the hash map-based solution stands out as the most efficient and practical choice. The key insight here is recognizing that using a frequency map allows us to efficiently count occurrences and check loneliness conditions in constant time for each element. This eliminates the need for redundant scans of the array. With a linear time complexity of O, n, and a manageable space overhead of O, n, this strategy provides the best balance of speed and memory usage. By comparison, the brute force approach is too slow with its O, n squared, complexity, making it infeasible for large inputs. The sorting-based method, while memory efficient, is hindered by its O, n log n, complexity, which makes it slower than the hash map-based solution. Ultimately, the hash map-based strategy is the clear winner, offering optimal performance and ease of implementation for this problem. To solve this problem, we need to identify all the elements in the array that appear exactly once and are not adjacent to any other numbers in the array. This means for each element x, we need to ensure that neither x1 nor x plus 1 is present in the array. The brute force approach begins by iterating through each element in the array. For each element, we check its frequency by counting how many times it appears in the array. If the count is not equal to 1, we can skip further checks for that element, as it does not meet the criteria. This is the first step toward identifying lonely numbers. Once we verify that an element appears exactly once, we then check its neighbors. Specifically, we need to confirm that neither x1 nor x plus 1 exists in the array. To do this, we can use a loop to search for these neighbors. If we find that both neighbors are absent, it means the element is isolated and satisfies the conditions to be considered a lonely number. At this point, we add the element to our result list. After processing all the elements in the array, we return the result list as the final output. However, while this brute force approach is simple to understand and implement, its time complexity is quite high. It involves two nested loops, where the outer loop iterates through all elements, and the inner loop handles counting and neighbor checks. This results in an overall time complexity of O, n squared, making it inefficient for large input sizes. The space complexity, on the other hand, is O, 1, since we only use a result list to store the output. Now, let's delve into the key insights behind this approach. First, counting occurrences is essential because the problem explicitly requires us to find elements that appear exactly once. Without this step, we cannot filter out elements that occur multiple times. Second, checking for neighbors ensures that the element is truly isolated. If either x1 or x plus 1 exists, the element cannot be considered lonely. Finally, while the brute force method is inefficient, it serves as a baseline for understanding the problem and confirming the correctness of our logic. It provides a clear, step-by-step way to solve the problem, even if it's not the most optimal solution. To improve the efficiency of our solution, we can leverage a hash map, which allows for O(1) average time complexity for both storing and looking up values. The optimized approach begins by traversing the array once to build a hash map that records the frequency of each element. This ensures that we can quickly retrieve the count of any number without iterating through the array multiple times. Once the hash map is constructed, we iterate through its keys. For each key, we check two conditions: whether its frequency is exactly 1 and whether its neighbors, x1 and x plus 1, are absent in the hash map. If both conditions are satisfied, we add the key to our result list. After checking all the keys, we return the result list as the output. This approach is not only more efficient but also easier to scale for larger input sizes. The optimized approach significantly reduces the time complexity compared to the brute force method. Constructing the hash map requires a single traversal of the array, which is O(n). Iterating through the hash map keys also takes O(n), as each key is processed once. Checking the frequency and neighbors for each key involves O(1) operations, thanks to the efficiency of the hash map. Combining these steps, the overall time complexity becomes O(n). In terms of space complexity, the hash map requires n additional space to store the frequencies. Optionally, we could use a hash set to store the array elements for quick neighbor checks, but the hash map already provides the same functionality. Therefore, the space complexity remains n, making this approach both time and space efficient. To better understand the optimized approach, let's walk through an example with the input array nums equals 5, 1, 2, 3, 4, 5. First, we build the frequency map, which results in 5, 2, 1, 1, 2, 1, 3, 1, 4, 1. Next, we check each key in the hash map. For the key 5, its frequency is 2, so we skip it. For the key 1, its frequency is 1, but one of its neighbors, 2, exists in the hash map, so we skip it as well. We then perform similar checks for 2, 3, and 4, finding that all of them have neighbors in the hash map. As a result, no elements satisfy the conditions to be lonely, and the output is an empty list. This demonstrates how the optimized approach efficiently processes the input to arrive at the correct result. The solution uses the counter class from Python's collections module to count the frequency of each number in the input list nums. This allows us to efficiently determine how many times a number appears in the array. The findLonely method iterates through each number in the array and applies two conditions to check if the number is lonely. 1. The number appears exactly once in the array, frequency, number, equals 1. 2. Neither its immediate predecessor, number 1, nor its immediate successor, number plus 1, exists in the array, frequency, number 1, equals 0 and frequency, number plus 1, equals 0. If both conditions are true, the number is added to the lonely_numbers list. Finally, the method returns the list of all lonely numbers. This approach is efficient, leveraging the frequency counter and avoids nested loops, ensuring the solution runs in n time complexity where n is the length of the input list. Here, we start by importing the necessary libraries, including java.util*, which will allow us to use data structures like hashmap and ArrayList. Inside the solution class, we define a method called findLonely that takes an integer array nums as input and returns a list of integers. The first step is to create a hash map called frequency map to store the frequency of each number in the input array. We use a for loop to iterate through the array, and for each number, we update its frequency in the map. The getOrDefault method is used to retrieve the current count for the number, defaulting to 0 if the number is not already in the map. After this loop, the frequency map will contain the count of each number in the array. Next, we initialize an array list called lonely numbers, which will store the numbers that meet the criteria for being lonely. We then iterate through the array again, and for each number, we check two conditions: first, whether the number appears exactly once in the frequency map, and second, whether its neighbors, number 1 and number plus 1, are not present in the map. If both conditions are true, the number is added to the lonely numbers list. These conditions ensure that the number is isolated in the array, both in terms of its frequency and its value relative to other numbers. Finally, we return the lonely numbers list, which contains all the lonely numbers found in the input array. Here, we start with the small input array nums equals 4, 3, 9, 2. The first step is to count the frequency of each number in the array using the counter class from Python's collections module. This gives us a frequency dictionary, frequency equals 4, 1, 3, 1, 9, 1, 2, 1, where each number appears exactly once. Next, we initialize an empty list called lonely_numbers to store the numbers that meet the criteria of being lonely. At this stage, the list is empty, and we proceed to check each number to determine if it qualifies as lonely. Now, we iterate through the input array nums and evaluate each number. Starting with 4, we see that it appears only once in the array, but its neighbor 3 exists. Therefore, 4 is not lonely. Next, we check 3, which also appears once, but it has a neighbor 2, so it's not lonely either. Then, we move to 9. It appears only once, and neither of its neighbors, 8 or 10, exist in the array. This means 9 is lonely, so we add it to the lonely_numbers list, which now becomes 9. Finally, we examine 2. While it appears only once, its neighbor 3 exists, so it's not lonely. The output for this example is 9. In this example, the input array is nums equals 1, 2, 3, 4, which contains consecutive numbers. We begin by counting the frequency of each number using counter, resulting in frequent equals 1, 1, 2, 1, 3, 1, 4, 1. As before, we initialize an empty list called lonely_numbers to store any lonely numbers we find. Now, we start iterating through the array. The first number is 1. It appears only once, but its neighbor 2 exists, so it's not lonely. Moving on to 2, we see it also appears only once, but it has neighbors 1 and 3, so it's not lonely either. For 3, we observe that it appears once as well, but it has neighbors 2 and 4, which means it's not lonely. Finally, for 4, it appears only once, but its neighbor 3 exists, so it's not lonely either. Since no numbers in this array meet the criteria for being lonely, the output for this example is an empty list. Now, we shift our focus to another example with a more diverse input array, nums equals 10, 6, 5, 8, 20. First, we calculate the frequency of each number using counter, which gives us frequency equals 10, 1, 6, 1, 5, 1, 8, 1, 21. As before, we initialize an empty list for lonely_numbers. Next, we iterate through the array nums, starting with 10. It appears only once, and neither of its neighbors, 9 or 11, exist, so 10 is lonely, and we add it to the list. The updated list is 10. Then, we check 6. While it appears only once, its neighbor 5 exists, so it's not lonely. For 5, we see it appears only once as well, but its neighbor 6 exists, so it's not lonely either. Now, we look at 8. It appears only once, and neither of its neighbors, 7 or 9, exist, so 8 is lonely, and we add it to the list. The updated list becomes 10, 8. Finally, for 20. We observe that it appears only once, and neither of its neighbors, 19 or 21, exist in the array. This means 20 is lonely, so we add it to the lonely_numbers list. The final list is 10, 8, 20. This concludes our process for identifying lonely numbers in this input array. The final output for this example is 10, 8, 20, which contains all the numbers that meet the criteria of being lonely. To analyze the time complexity of our solution, we start by breaking it into key steps. First, we count the frequencies of all elements in the array using the counter nums operation. This involves iterating through the entire array once, so its time complexity is O(n), where n is the number of elements in the array. Next, we iterate through the array again using a for loop. For each element, we perform constant time operations, such as checking the frequency of the element itself and its immediate neighbors. Since these are dictionary lookups, they each take O(1) time on average. This makes the total time for the loop O(n). Combining both steps, we see that the overall time complexity of the solution is O(n) plus O(n), which simplifies to O(n). Now let's shift our focus to space complexity. The primary contributor here is the frequency dictionary created by counter nums. In the worst-case scenario, where all elements in the array are distinct, the dictionary would store one key value pair for each of the n elements. This requires O(n) space. Additionally, we have the result list, lonely_numbers, which stores the lonely numbers. If all elements in the array are lonely, this list would also hold up to n elements, requiring another O(n) space. Beyond these, auxiliary space is limited to a few variables like number and frequency, which only require O(1) space. When we combine all these components, the overall space complexity becomes O(n) plus O(n) plus O(1), which simplifies to O(n). Combining our time and space analyses, we see that both complexities are linear, or O(n), making the solution efficient. To put this in perspective, consider a brute force approach. A naive method would involve manually iterating through the array and checking the frequency of each element and its neighbors. For each of the n elements, this would involve O(n) operations, resulting in a time complexity of O(n squared). In contrast, the optimized approach leverages a hash table to store frequencies, enabling O(1) lookups for each element and its neighbors. This reduces the time complexity to O(n), which is a significant improvement, especially for larger input sizes. Finally, let's evaluate the algorithm's performance across different scenarios. In the best case, we still need to iterate through the entire array and perform constant time operations for each element, resulting in a time complexity of O(n). The average case is similar, as each element and its neighbors are processed in constant time, leading to an O(n) complexity. Even in the worst-case scenario, where all elements are distinct and require neighbor checks, the complexity remains O(n). This consistency across best, average, and worst cases highlights the efficiency of the solution, with both time and space complexities consistently at O(n). When tackling this problem, there are several common mistakes to watch out for. First, failing to account for duplicate elements in the array can lead to incorrect results. For example, if you check whether a number appears without ensuring it exists exactly once, you might mistakenly include it in your output. Next, inefficient handling of the x1 and x+1 checks is another pitfall. A naive approach might repeatedly search for these values in the array, resulting in time complexity of O(n squared). To avoid this, you can use a hash set for constant time lookups. Additionally, it's important to consider edge cases. Scenarios like an empty array, arrays with all duplicates, or arrays containing only a single element can break your solution if not explicitly handled. Another mistake is assuming the array is sorted when it isn't. Unless sorting is explicitly allowed, making this assumption can lead to undefined behavior. Finally, overcomplicating your logic with nested loops or redundant checks can increase the likelihood of bugs. Simple, efficient solutions are often more robust and easier to debug. Now, when it comes to interviews, there are a few important insights to keep in mind. One key aspect of this problem is recognizing patterns, such as identifying unique elements or ranges. Data structures like hash sets or hash maps are often the cornerstone of efficient solutions since they allow for O(1) lookups. Interviewers typically expect you to move beyond brute force approaches, which, while simple to implement, are suboptimal. Optimized solutions, such as those using a hash set or sorting, are usually preferred. It's also crucial to clarify constraints during an interview. For instance, ask about input size, whether negative numbers are allowed, or if sorting the array is permitted. These details can significantly influence your approach. Lastly, be prepared to discuss trade-offs. For example, you might compare the time complexity of O(n) solutions with O(n log n) alternatives or weigh the space complexity of using a hash set versus maintaining an in-place solution. Familiarizing yourself with related problems such as LeetCode 217, 136, 128, or 448 can also help you identify recurring themes and apply similar strategies. To wrap up, let's explore some alternative approaches and their trade-offs. The brute force approach involves iterating through each element and directly checking the conditions for loneliness. While this method is straightforward, it's inefficient for large arrays, with a time complexity of O(n squared). It's best suited for small inputs or as a starting point when brainstorming solutions. A more efficient option is the hash set approach. By storing elements in a hash set, you can check for x1 and x+1 in constant time, reducing the overall time complexity to O(n). However, this comes at the cost of O(n) space. Another technique is the sorting approach, where you sort the array first and then iterate to identify lonely numbers. This introduces an O(n log n) overhead but reduces space complexity to O(1) if the array is sorted in place. Finally, the two-pointer method is another efficient option for sorted arrays. This technique minimizes space usage, requiring only O(1) extra space, and is particularly useful for detecting sequences or gaps. However, it's only applicable when sorting is allowed or the array is pre-sorted. Each of these approaches has its strengths and weaknesses, so the best choice depends on the specific constraints and requirements of the problem. Great job following along. To summarize, we tackled problem number 2150 and reviewed approaches to solve it. Keep practicing these types of problems to sharpen your skills. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!